CO2. So let's go to the oxidation reaction. Okay, in the oxidation reaction, okay, it is divided to mild oxidation and strong oxidation. So mild oxidation, when we react it with the KMnO4, it's either in the basic medium or in acidic medium. Okay, but if it is occur at the room temperature and below, so we say that they are mild oxidation, then the product of this mild oxidation will be diol. Okay, 2 hydroxyl group attached to the carbon-carbon double bond. And the observation for this mild oxidation, okay, is the purple color of the potassium permanganate will turn to cloudy brown precipitate to show the presence of the Mn4+, okay, to show the production of the Mn4+. As for the strong oxidation, okay, it is the reaction with the KMnO4 as well, but it has to be in the acidic medium, and also the condition must be heat. Okay, so the product of this strong oxidation is either we will get a carboxylic acid, okay, or we also can get a ketone, okay, or carbon dioxide plus H2O, depends on our alkene. So let me show you the example how to write the chemical equation of the reaction. So if let's say we have a ethene just now, CH2, double bond CH2. Okay, so when it is reacted, in number 1 with the KMnO form, okay, it's either it is in acidic or basic. You just choose either one. So if I put it as a H plus, means that it is acidic. The condition is room temp. So we know that this is a cold. Okay, so it will be production of the diol. So the product will be CH2, CH2, 1 hydroxyl attached to the first carbon, and then another 1 hydroxyl attached to the second carbon. Okay, this is for the mild oxidation. As for the strong oxidation, okay, it is reacted with the KMnO4. It must be in H plus and heat. So what happened is, okay, since that we have to focus on our carbon-carbon double bond. Okay, so the left side we have CH2, the right side also CH2. So initially what happened is, okay, it is actually forming C double bond O, O, H. Okay, so since that we are having symmetrical alkene, both sides will turn to COOH or methanoic acid. Okay, so we have 2 methanoic acid. However, this methanoic acid is not stable and it will further oxidize in this strong oxidation condition, so that it is then finally produce carbon dioxide plus H2. Okay, so basically, okay, the strong oxidation of this, okay, with the KMnO4, H plus and heat will produce carbon dioxide plus H2O. You don't need to show the intermediates. Okay, this is if it produce carbon dioxide and H2O. Let's look at two other alkene, okay, that can produce carboxylic acid and also ketone. Okay, let me show you the example. If let's say we have a CH3, CH, double bond, CH3, CH. Okay, so if it is undergo mild oxidation, okay, with the KMnO4, OH minus, for example, cool or room temperature, they are the same. So that it will produce CH3, CH, single bond, C, CH3, CH3. So focus on this carbon-carbon double bond initially. Now it is turns to diol when two hydroxyl group attached to these two carbon. Okay, then the next one, if it is reacted with the in the strong oxidation with the KMnO4 H plus and heat. Okay, so focus on the carbon-carbon double bond. Okay, so this side, okay, we have a secondary carbon. Okay, this carbon-carbon double bond is secondary carbon when it attached to two neighbor carbon. So when this is a secondary carbon, it will turn to carboxylic acid. As for this carbon-carbon double bond, okay, it is actually tertiary carbon, okay, because this carbon is attached to 1, 2, 3 neighbor carbon. So the tertiary carbon will turn to ketone from this oxidation. Okay, so how to do it? Okay, so this side, okay, see the carbon, the secondary carbon. Okay, focus on the position of the double bond here. Okay, just rewrite back. It will turn to CH3, C double bond O. Okay, and H also having or getting one oxygen attached to it. Okay, so this is the carboxylic acid. So the secondary carbon will turn to the carboxylic acid. So now focus to the right side. Okay, this carbon is the tertiary 1, 2, 3. So this carbon, okay, we just rewrite back the structure. It will be CH3, CH3, and then double bond we add with the oxygen. Okay, so if we rearrange back this structure, it is actually CH3, C double bond O, CH3. It is a ketone. Okay, as for this one, okay, we rearrange it back. It is actually CH3, C double bond O, OH, carboxylic acid. So to predict the product of the strong oxidation, okay, we actually need to identify the type of the carbon-carbon double bond. In this case, okay, the first example just now, ethene. Okay, both of the carbon are primary carbon. So look at to this carbon, it is only attached to one carbon, so it is primary. As for the second carbon double bond, it is also a primary carbon because it only has one carbon attached to it. So the product of the strong oxidation of the primary carbon double bond will produce a carbon dioxide plus H2O. Okay, the primary will produce CO2 plus H2O. As for the secondary carbon, as this side, it will turn to carboxylic acid. And tertiary carbon, as for this side, okay, it will turn to ketone. Okay, so we have to remember on this. Next, this is the last part of this of alkene, which is the mechanism, okay, that involve the alkene reaction. Okay, the specific name for the mechanism that we covered in our syllabus is the electrophilic addition. Okay, in which we can use this mechanism, okay, to show the process for addition reactions that we have for the alkene. Okay. So if you have your textbook, you can refer to the page of 163, okay, that shows the general mechanism. So from the textbook, 163, okay, you should know that, okay, this electrophilic addition reaction occur in two steps, okay. The first step is the formation of the carbocation. Remember, the carbocation is the carbon that are having positive charge. Okay, and then the second step is the rapid reaction of the carbocation with the negative ion. The reaction between the carbocation, okay, with the negative ion. Okay, let me show you the first example, okay, which is the first reaction of the alkene. Okay, is the halogenation in inert solvent. If we write the general equation of a reaction for this reaction, it will be CH2 double bond CH2 react with the chlorine, for example, in CH2 Cl2, and the condition is the room temp. Okay, we know that the product will be CH2Cl, CH2Cl. This is the general chemical equation. So we want to see how this is produced, okay, in this reaction by looking at the electrophilic mechanism, okay, the electrophilic addition mechanism. So the first step, okay, which is the production of the carbocation ion, the formation of the carbocation ion. Okay, we start with the ethene here, okay, and then it is reacted with Cl2. So we have Cl, Cl, bonded. Okay, so firstly, okay, the electron from the carbon-carbon double bond will attack the first chlorine. Okay, it makes the bond cleavage occur here between these two atoms of chlorine. So this is what we call as the heterolysis. Okay, in which both of the shared electron here, okay, goes to this chlorine. Okay, so this chlorine is then attached to one of the carbon. Okay, so it will form this. If let's say the chlorine is attached, this chlorine is attached to this carbon, so we will have this arrangement, and it will mix the second carbon become carbocation. Okay, and then this chlorine will then turns to Cl minus. Okay, and then in the second step, okay, this Cl minus or this negative ion will attack the carbocation here. Okay, so it will attack to this carbocation, so it will then attach to it. Okay, and then now we have two chlorine attached to the carbon-carbon double bond. Okay, so now it turns to carbon single carbon with one chlorine each. Okay, this is the electrophilic addition reaction. It is the same thing that is happened. Okay, let's say we have a reaction of the hydrogenation. Okay, let me show you the example. Hydrogenation reaction of ethene. So we start with the CH2 double bond. CH2 react with the hydrogen. Okay, so firstly, what happened is this electron from the double bond will attack one of the hydrogen, and then the heterolytic cleavage occur, goes to another one hydrogen, and then it is producing carbocation ion CH2, H, CH2 plus. And then this hydrogen is turning to, this turns to H minus. Okay, this is the first step. Okay, I rewrite back in the second step. Okay, what happened is this carbocation ion reacted with this negative ion. We have a CH3, CH2 positive. Okay, I condense the structure. React with the H minus. Okay, arrow is compulsory. We shows the reaction. So H minus attack the carbocation ion, and it turns to CH3, CH2, H attached to it. Or if we condense it, it is actually the same as CH3, CH3. Okay, and then for the hydration reaction, okay, the same reaction. For the hydration, it is actually the reaction with the H2O, right? So HOH. Okay, so when this electron, okay, attack H, so what happened is the cleavage occur. It makes the OH receive both of the shared electron. Okay, so that now this side will turn to OH minus. Okay, and then OH minus in the second step will attack the carbocation ion. Okay, so it produced OH here, and then this is actually CH2O. It is also happen when we have the hydrohalogenation reaction, let me rewrite the new equation. So if let's say we have ethene, CH2 double bond, CH2 react with the HBr. Okay, so first step is this electron attack H, cleavage occur, goes to bromine. It is then produced CH2, CH2, H here. Another one carbon turns to the carbocation with the bromide. Okay. And then in the second step, okay, I condense this structure so that it is actually turns to CH3, CH2 plus, react with the Br minus, okay, in which the bromide attack the carbocation, so it will turns to CH3, CH2, Br. Okay. So this is for the mechanism. Okay, it is simple for the symmetrical alkene. Okay, but if we have an unsymmetrical alkene, we start to considering on the Markovnikov, okay, rules. Let me try to show you example of the example. If let's say we have a unsymmetrical alkene, okay, if we have a ethene, CH3, CH double bond C, H2. Okay, it is then reacted with HBr. Okay, so the first step is this electron will attack H, and then heterotic cleavage occur. So there are two possibilities. It's either the hydrogen is attached to this carbon or the hydrogen attached to the first carbon. So we have to draw both possibility. Okay, so that it's either it turns to CH3, CH, single CH, CH, H attached to it. This carbon become carbocation, or this turns to CH3, CH, CH, H, H. This is the initial structure. And the hydrogen is attached to this carbon, makes the second carbon become carbocation. Okay, don't forget to have a bromide as the side product of the first step. Okay, so here add with the Br minus, and this one Br minus. Okay, in the second step, okay, there is when we have a bromide that attacking the carbocation. Okay, so this bromide attack the carbocation. Since that we have two possible carbocation, okay, this one or this one, so we will have two products. Okay, in which, since that I have no enough space, so let me show you for the first one, the first possibility. Okay, the product will be CH3, CH, H, CH, H, Br. Okay, and for the second one, okay, the product will be CH3, C, H, CH, H, H, Br. Okay, so according to the Markovnikov rules, okay, the major product is when the hydrogen is attached to the carbon that have more hydrogen initially. So obviously, okay, between these two carbon, carbon 1 and carbon 2, okay, carbon 1 is actually having more hydrogen. Okay, so the major product will be this one. Major, minor. But actually, what is the actual reason, okay, that makes this one become a major product is actually because of the stability of the carbocation that is produced in the first step. Okay, so if you look at to this carbocation, we are focusing on that carbon. Okay, we compare this carbon and this carbocation. Okay, this carbocation is actually the secondary carbon. Okay, see, look at to this carbon, it is attached to two neighbor carbon. So this carbocation is under the category of the secondary carbocation. And when we look at to this carbocation, it only has one carbon, one neighbor carbon attached to it. So this carbocation is the primary carbocation. Okay. So the secondary, basically the secondary carbocation is more stable than the primary. So when this intermediate or this carbocation is more stable, means that we have more this, okay, that is produced in the first step. Okay, that is why the product will be the major product. Okay, let me show you the ranking of the carbocation. Tertiary carbocation is more stable than the secondary carbocation, and it is more stable than the primary carbocation. It means that the tertiary carbocation will produce a major product as compared to secondary. Okay, and if let's say we have a secondary and primary only, so the secondary will lead to major product. So I think that's all on the alkene. So I hope that you can do your tutorial. Okay, you can start completing your tutorial too. See you. Assalamualaikum.